In today's video, we will look at the mathematical definition of electric flux, an example of how to calculate electric flux, and then applying those calculations to using Gauss's law. First, let's review what we've already learned. If we are given a surface, in this case a piece of paper, we're looking at it edge on, and place it in an electric field, we can define an electric flux associated with that surface. It's basically a way of counting the number of field lines that pass through the surface. However, to decide whether the flux is positive or negative, we first need to define an area vector. If the area vector and the field lines point in roughly the same direction, the flux is positive. If they point in roughly opposite directions, the flux is negative. And if, as in this case, when looking at this surface, if the field lines are tangent to the surface, which means they are perpendicular to the area vector, then the flux is zero. This kind of behavior, where we get a positive number if two vectors point in roughly the same direction, a negative number if they point in roughly opposite directions, and zero if they are perpendicular to each other, reminds us of something. And that is the dot product. And in fact, that is exactly what we use to define the electric flux. The electric flux through a surface S is defined as the integral of E dot dA over the surface S. As usual, the dot product can be expanded in terms of magnitude of E times magnitude of dA times cosine of the angle between them. Remember that this is the angle between the electric field vector and the area vector, not the angle between the electric field and the surface. So if an electric field is tangent to a surface, there is 90 degrees between the electric field vector and the area vector. We can also rewrite this as the integral of E perpendicular times dA, where E perpendicular is the component of the electric field that is perpendicular to the surface, that is perpendicular to the area. Why does this definition make sense? Let's take a closer look. If we have this green surface and these blue electric field lines, then at each point where the field lines pass through the surface, we can find the electric field vector by taking the tangent to the electric field line. So these orange vectors are the electric field vectors. Let's focus on one example in particular. We take this electric field vector and notice that the angle between the electric field vector and the normal is theta. Remember, the normal is the perpendicular to the surface. As such, E cosine theta is the component of the electric field that lies along the normal, that is, in the same direction as the area vector. And E sine theta is the component of the electric field that lies tangent to the surface, that is, perpendicular to the area vector. We know that an electric field tangent to the surface does not contribute to the flux, so we can ignore E sine theta. So the only component of the electric field that does contribute to the flux is E cosine theta. But E cosine theta times dA can just be written as E dot dA. Let's look at an example of calculating the electric flux. We are given an electric field. Notice that this field is not constant. It is a function of y, and it has components in both the x direction and the y direction. Our surface is a square, which we will call S, and the side of the square has a length of 2 meters, and the square is placed in the YZ plane, extending from y equals 0 to y equals 2 and z equals 0 to z equals 2. We are asked to find the magnitude of the flux through this square S. Since the square is in the YZ plane, we can choose either plus I or negative I as the direction of dA, since both of these are perpendicular to the plane in the YZ plane. We will choose plus I hat. So our dA is dy times dz times I hat. I hat gives us the direction, which is perpendicular to the YZ plane, and dy and dz give us a small area. Now let's try and evaluate the integral. We substitute for E and for dA, and then we note that we are doing a dot product. Since the dot product of j hat and I hat is 0, we only need to worry about the dot product of I hat with I hat. I hat dot I hat is 1, and so only this component of the electric field survives, 1 plus 2y. We separate the dy and dz, put the appropriate limits on the integrals, and then do the y integral first, evaluate it, and then do the z integral. And this is our final answer. Feel free to pause the video and look through the steps carefully. Notice that we could have done the integrals in the other order as well. It would not have made a difference. Gauss's law tells us that the total electric flux passing through a closed surface S is equal to the charge enclosed by that surface S divided by epsilon naught. While Gauss's law is always true, it's not always easy to use. We typically use Gauss's law when the charge distribution we are looking at has some symmetry, which allows us to greatly simplify the integrals. There are only 3 types of symmetry that we will use. The first is spherical symmetry, which covers solid spheres, hollow spheres, spherical shells, and point charges. The second is cylindrical symmetry, which covers infinitely long wires, infinitely long cylinders, whether solid or hollow. And the third is planar symmetry, which covers infinite planes. Even though in real life we rarely come across infinite cylinders or infinite planes, it turns out that these are often good approximations. If we are very close to a large plane, for example, we can treat it like an infinite plane. Or if we are very close to a very long wire, we can treat it like an infinite wire. Here are the steps to using Gauss's law. We first identify which of the 3 symmetries we can use. We then identify the point of interest, for example, the point where we want to find the electric field. We then draw a Gaussian surface of the correct symmetry such that it passes through the point of interest. So if the charge has spherical symmetry, our Gaussian surface will also be a sphere, passing through the point of interest. We calculate the flux in terms of the field and the area of the Gaussian surface. We calculate the charge enclosed, which sometimes we might need to express in terms of the charge density. And then we equate the corresponding quantities using Gauss's law and solve for the unknown. Let's look at an example. Consider a hollow spherical shell of charge of radius r and charge q. It's a uniformly distributed charge q over this hollow spherical shell of radius r. We are interested in finding the field at the points P1 and P2. O here is the center of the sphere. Let us start with finding the field at point P1. Whenever we want to use Gauss's law, we have to start by drawing a Gaussian surface. Since here the charge has spherical symmetry, our Gaussian surface is also a sphere. We will call it S1. I have drawn it with that dashed line to remind you that it is simply an imaginary surface. Notice that since we want to find the field at point P1, we choose to draw our Gaussian surface so that it passes through P1. The green arrows represent the area vectors at various points. As usual, they are perpendicular to the surface, and since the sphere is a closed surface, they point outward. We expect that if there is any field inside the spherical shell, it must point radially. In other words, any electric field lines must go like this. We can see that the direction of these field lines is in the opposite direction to the area vectors. In other words, the angle between them is 180 degrees. Let us calculate the flux. We have to calculate this integral. We expand the dot product. We substitute for the angle. Since everywhere along the sphere the angle is 180 degrees, we can put that in there. And since cosine 180 degrees is -1, we end up with this integral. Now, here is where the symmetry comes into play. Because our Gaussian surface has the same symmetry as the charge distribution, we expect that everywhere along the Gaussian surface, the field has the same strength. It will not have the same direction, but it will have the same strength everywhere along the Gaussian surface. Because of this, we can treat E1 as a constant on the surface S1. Because it's a constant, we can pull it out. And we are left with E1 times the integral of dA along S1. But the integral of dA along S1 is simply the area of S1. So we finally arrive at E1 times A. This is why we say symmetry is so important when using Gauss's law. It is the use of symmetry that allows us to extract E1 to outside the integral and reduce our integral to simply E1 times A. If the charge was not spherically symmetric, if some parts of the sphere had more charge than others, we would not be able to do this. Finally, we plug in for the area of a sphere. In this case, this is the area of the Gaussian surface. So we write 4 pi r1 squared, where r1 is the distance from O to the point P1. This is our result for the flux passing through the Gaussian surface S1. We are now ready to put this in to Gauss's law. We have evaluated the left-hand side, that is the flux passing through the Gaussian surface. Now we need to look at the right-hand side. We need the charge enclosed by the Gaussian surface. But since the Gaussian surface is inside the hollow spherical shell, it does not enclose any charge. All the charge is outside of the shell. So the charge enclosed is 0, and the right-hand side evaluates to 0. Solving for E1, we find that E1 is 0. And so we have very quickly proved a remarkable result, which is if you have a uniformly charged spherical shell, a hollow spherical shell of charge, then inside the spherical shell, the electric field is 0. Everywhere inside the spherical shell, not merely at the center of the shell, but everywhere inside the hollow spherical shell, the electric field is 0. Let us now find the field at point P2, which is outside. Once again, since the symmetry is spherical, we surround our charged shell by a spherical Gaussian surface. Since we want to find the field at the point P2, our sphere passes through the point P2. We call this Gaussian surface S2. It has a radius R2. We expect that if there are electric fields outside the shell, then they will point radially outward because of the symmetry of the shell. Looking at the little area vectors, we know that they point in the same direction as the electric field, and so the angle between them is always going to be 0. Once again, we calculate the flux, expand the dot product, substitute for the angle. Since cosine of 0 is 1, it simplifies to integral E2 dA. Again, using symmetry, we can say that E2 is constant along the surface S2, and so it can be pulled out. And finally, the integral simplifies to E2 times A, which is E2 times 4 pi times R2 squared. This is the left-hand side of Gauss's law, and now we evaluate the right-hand side. In this case, our Gaussian surface encloses all the charge on the spherical shell. So the charge enclosed is Q. And the right-hand side becomes Q over epsilon naught. Setting this equal to E2 times 4 pi R2 squared and solving for E2, we get E2 is equal to Q over 4 pi R2 squared times epsilon naught. Notice that we can rewrite this as kq over r2 squared. This leads us to another remarkable result. If you are outside a spherical shell of charge, a uniform spherical shell of charge, then the electric field created by that shell outside the shell is the same as that of a point charge. So you can replace that spherical shell by a point charge with the same charge centered at the center of the original shell. This, of course, only holds if you are outside the shell. What we have calculated so far is simply the magnitude of the electric field. To turn it back into a vector, we multiply this magnitude by the direction of the area vector, which we noted before was pointing radially outward in the r hat direction. And so here is our final expression for the electric field due to a uniformly charged hollow spherical shell when looking at a point outside the shell. If we were to combine our two results and plot the radial component of the electric field as a function of distance from the center, this is what we would get. The field is 0 as long as you are inside the shell, and then once you go outside, it jumps up and then starts decreasing as 1 over r squared. Let us look at another example. Here we consider a solid sheet of charge. This sheet has thickness d and a volume charge density ρ. That is, ρ is the charge per unit volume. The sheet is centered at the origin and placed in the xy plane. We are interested in the field at point P2, which is a distance z from the xy plane. Here the symmetry is planar symmetry, and we use a Gaussian surface that looks like a box. It is sometimes called a Gaussian pillbox. Here I show the sheet as well as the pillbox in cross-section. This face of the pillbox has an area A. Here it is again in a bit more detail. I have marked the dimensions of the pillbox. It has a height h, length l, and a thickness 2z. It extends to both sides of the sheet. We call this Gaussian surface S2. From the planar symmetry of the charge, we expect that the electric field lines point away from the sheet, assuming the sheet is positively charged. Now, let us look at where the flux is. Notice that the top and bottom surfaces, as well as the side surfaces of the Gaussian pillbox, since they are parallel or tangent to the electric field, do not have any flux passing through them. Instead, only this face and this face have flux passing through them. What about the area vectors? The area vector here points outward like this. The area vector here points outward like this. In both cases, we see that the area vector and the local electric field point in the same direction, so the angle between them is 0. When we do our integral, we will have to keep in mind that there are two faces through which the electric flux passes. We set up our integral, expand the dot product, plug in theta equals 0, which simplifies our integral. Realize that the electric field is constant along the face of the Gaussian pillbox and pull it out, and then integrate. The factor of 2 is because there are two faces, each with area A, that have flux passing through them. The area of the face is h times L. Having evaluated the left-hand side, we now focus on the right-hand side. We need to find the charge enclosed by our Gaussian pillbox. The charge enclosed can be found by multiplying the volume charge density ρ, that is the charge per unit volume, by the volume enclosed. The volume enclosed by our Gaussian pillbox, that is the volume where there is charge present, is d, the thickness of the sheet of charge, times h times L. dHL times ρ will give us the charge enclosed, and that divided by epsilon naught gives us the right-hand side of Gauss's law. Setting these two sides equal to each other, we solve for E2 and find that it is ρd divided by 2 epsilon naught. Notice something very important. The dimensions h and L of the Gaussian pillbox in the end cancelled out. They did not matter. This is very important because the Gaussian pillbox, remember, is simply an imaginary construction. It would not make sense if the dimensions of this imaginary box somehow affected what the actual field was. So it is good that they cancel out. Once again, all we have found so far is the magnitude of the electric field. To turn it back into a vector, we multiply our result by the direction of the area vector, which was in the z direction at point P2, that is k hat. If we were on the other side of the sheet, it would be in the negative k-hat direction. Now let us try finding the electric field for the same situation of charge, but at a point P1 which is inside the sheet. The point P1 is a distance z1 from the central plane. As before, the thickness of the sheet is d, and we set the height of our Gaussian pillbox to h, and we mark this Gaussian surface as S1. We expect, again, that the electric field will point like this, away from the central plane. At the center, we expect that the field is 0, because there are equal amounts of positive charge on either side, and so the field would cancel out in the center. But as soon as you start moving away from the center, the field would start increasing. Once again, we note that the direction of the field is the same as the direction of the area vectors on those faces. And so the angle between them is 0. We set up our integral, expand the dot product, plug in for the angle, and once again use symmetry to argue that E1 is constant along the Gaussian surface and pull it outside. Once again, there are two faces, each of area A, that have flux passing through them. So our final result is 2E1 times A, and plugging in for A, we get 2E1 times HL. We now evaluate the right side of Gauss's law. Once again, we can find the charge enclosed by looking at the charge density ρ times the volume enclosed. This time the volume enclosed is 2z, which is the thickness of the Gaussian box, times h times L. That times ρ gives us the charge enclosed. And so equating both sides, we have E1 times 2HL is equal to 2 rho z HL divided by epsilon naught. Solving for E1, we find that E1 is equal to rho z divided by epsilon naught. Once again, this is simply the magnitude, and by adding on the direction of the area vector, we recover the entire electric field at point P1, and we see that it is pointing in the positive z direction at point P1, and on the other side it would point in the negative z direction. Once again, if we plot the z component of the electric field in this case as a function of z, starting from the center where the field is 0, we see that the field increases linearly because the electric field is a linear function of z until we reach z equals d over 2, which is where the sheet ends. And once we go outside the sheet, we find that the field is constant, which is not surprising since this is basically a combination of several infinite sheets of charge, and we know that for an infinite thin sheet of charge, the field is constant. By layering a few of them together, the field still remains constant. That is it for this video, and I'll see you in the next.